Hello everyone. This is Qi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Today, we're starting with Chapter 1, titled Introduction to Deep Learning and TensorFlow Installation. Let's begin our exploration of deep learning together. Before diving into the content, let's clarify the learning objectives of this chapter. By the end of this chapter, you will grasp 5 key points. First, the basic concepts of deep learning. Second, the relationship and differences between deep learning, AI, machine learning, and regression. Third, how to set up the development environment with TensorFlow and Keras. Fourth, the evolution of deep learning. And fifth, the fields where deep learning excels. Now, let's move to part 1.1. The focus of this part is to clarify the concepts and connections between 3 core terms: machine learning, deep learning, and AI. We'll break down each concept step by step to help you build a clear understanding. First, let's talk about machine learning. A classic definition comes from Professor Tom Michael Mitchell of Carnegie Mellon University, who stated in his 1997 book Machine Learning, if a program can improve its performance P on a task T as its experience E increases, then it is capable of learning from experience. Machine learning can be mainly divided into 2 types: supervised learning, which uses labeled training data to learn and judge unlabeled data, and unsupervised learning, which learns data features from unlabeled training data. Next up is deep learning. It is a sophisticated machine learning algorithm originating from the study of artificial neural networks, and it emphasizes learning through consecutive layers. The deep here refers to the number of layers in the neural network, while learning means the training process of the network. The key difference between deep learning and machine learning lies in feature extraction. Deep learning can automatically extract abstract features, whereas machine learning mostly relies on manual feature selection and construction. Now, let's sort out the relationship between AI, machine learning, ML, and deep learning, DL. Artificial intelligence, AI, is a science that studies creating intelligent machines or systems to simulate and extend human intelligent activities. As shown in the figure on this page, their relationship is hierarchical. AI is the broadest field, ML is an important branch of AI, and DL is a subset of ML. The figure also lists specific technologies under each category, helping you visualize this structure. After understanding the relationship between AI, ML, and DL, we move to part 1.2, which focuses on the connection between deep learning and regression analysis. This part will help you understand deep learning from the perspective of traditional regression analysis, making the complex concept more accessible. First, let's review the basic framework of regression analysis. As shown in the formula on this page, it is expressed as y equals f x epsilon. Here, y is the dependent variable we want to predict, x is the independent variable, input data, f represents the functional relationship between x and y, and epsilon is the error term that accounts for uncaptured factors. This framework is the basis for linking regression analysis with deep learning. In fact, deep learning is a highly complex nonlinear regression model, and it fully fits the y equals f x epsilon framework we just mentioned. Let's take the HowOld.net tool, which predicts age and gender from faces, as an example. Images are stored as pixels. For instance, a 1024 multiplied by 1024 multiplied by 3 image has 3 pixel matrices, each with 1,048,576 pixels. From a modeling perspective, a neural network is essentially a nonlinear regression model. Given input x, like face pixel data, it outputs a predicted value y equals f x. Theta, where theta is the parameter to be estimated. In practice, theta can be extremely high-dimensional, even reaching hundreds of millions. Now, let's turn to part 1.3, the evolution of deep learning. Understanding the development history of deep learning can help us better grasp its current status and future trends. In this part, we'll divide the development of deep learning into three key phases for detailed introduction. The development history of deep learning is divided into three phases. Phase 1 is the germination period 1940 seconds to 1980 seconds. In 1943, American neurophysiologist Warren McCulloch and mathematician Walter Pitts proposed the MP model artificial neuron model by simulating biological neurons. Phase 2 is the development period 1990 seconds to 2011. In the 1980s, Rosenblatt's backpropagation (BP) algorithms solved linear inseparability for multilayer perceptrons. In 1989, Jan Leisuan used BP to train networks for handwritten postal code recognition, marking the birth of convolutional neural networks (CNN). Phase 3 is the boom period 2011 to present. Key milestones include AlexNet 2012, VGGNet and Inception 2014, ResNet 2015, and MobileNet and DenseNet 2017. Next is Part 1.4, Fields where Deep Learning excels. Deep learning has achieved remarkable results in many practical fields. In this part, we'll focus on several core fields and their typical applications to show you the powerful capabilities of deep learning. The first field we'll cover is image processing, which uses computers to analyze images for desired results. Its main applications include image classification, object detection, and image segmentation. As shown in the figure on this page, object detection can identify objects like person, dog, horse, car, and cat in images, with high confidence scores all above 0.98, demonstrating its high accuracy. Continuing with fields where deep learning excels, besides image detection we mentioned earlier, image processing also includes image segmentation, dividing images into meaningful regions, and style transfer, applying one image's style to another. Another important field is speech recognition, which enables machines to recognize and understand speech signals, converting them into text or commands. Common examples are smart assistants like Tiamagini, iFolly, and Siri shown here. Additionally, natural language processing (NLP) allows computers to process, understand, and use human language, with applications like text classification, sentiment analysis, and machine translation. Now, let's enter Part 1.5, Installing TensorFlow. To practice deep learning, we first need to set up the development environment. The core tools here are TensorFlow and Keras. TensorFlow is an open-source library by Google, using computational graphs for numerical computations, widely used in ML and math-intensive algorithms. Keras is a concise Python-based deep learning framework highly encapsulated, allowing you to build neural networks with a few lines of code, and most of its functions are integrated into TensorFlow. For hardware preparation, you can choose CPU training, GPU training, or cloud-based GPU training, which we recommend. For software, the easiest way to install TensorFlow is using Anaconda. Let's detail the steps to install TensorFlow and Keras in the Anaconda environment. First, install TensorFlow, open the command line, and enter conda install TensorFlow GPU for GPU support, which automatically installs TUDA and other dependencies, or conda install TensorFlow for CPU. After installation, verify it, enter Python in the command line, then run test code like importing TensorFlow and creating a session. As shown in the code snippet here, import TensorFlow as tf. Ses equals tf. Session. To install Keras, simply enter conda install Keras in the command line. Anaconda will handle the installation automatically. After installing TensorFlow and Keras, we usually use Jupyter Notebook to run deep learning code. Jupyter Notebook is a web-based interactive computing application that covers the entire process: development, documentation, code execution, and result presentation. There are two main ways to launch it. First, launch directly through the Anaconda interface. Second, enter Jupyter Notebook in the server terminal to start the web version. The interface shown here lets you write and run code interactively. For example, the code import TensorFlow as TF constant 3, 4, 1, 5, summa equals TF. Reduce underline, sum, a. Session equals TF. Session, print session. Run, summa outputs 13, showing real-time results. Note, this page supplements the Jupyter Notebook content. As we just mentioned, Jupyter Notebook's interactive mode is very convenient for deep learning practice. The web interface here shows a typical usage scenario. You can create a new notebook, select the Python 3 kernel, and then write code step by step. When you run the code to import TensorFlow, define constants, calculate sums, and use a session to get results, you can see the output immediately. This helps you test code snippets quickly and adjust your models in real time, making it an essential tool for learning and developing deep learning projects. Finally, let's look at the exercises for this chapter. They will help you consolidate what you've learned. The exercises are as follows. First, after studying this chapter, what do you think are the reasons for the rise of deep learning? 2. What are the differences between deep learning and machine learning? 3. Besides the fields mentioned, look up information to find other fields where deep learning excels. 4th, try installing TensorFlow and Keras in the Ubuntu system. 5th, write Python code to calculate the sum of two matrices. Take your time to complete these exercises, and if you encounter problems, you can review the chapter content or ask for help.